I'm Grandma Books, and I'm so glad you're back for another kitchen experiment. These are science fun experiments in my kitchen, and it's a lot better to have science in my kitchen than in the laboratory because then we get to eat some of the experiments. So today we're going to talk about solids, and we learned about density, and some things are more dense than others, and solids are usually more dense than liquids, and very often more dense than gases. But different solids have different density. I've got a little rock here, and rocks are heavy and very dense. And I've got a marshmallow, and marshmallows are very light. So even though this is heavier, it's much lighter. And we're going to do some experiments with marshmallows. I'm predicting that marshmallows have a lot of air in them. Now, I don't know if that's true, but I think it is. So here's an experiment we're going to do. Ask your mom to put a marshmallow on a paper towel and put it in the microwave for 30 seconds. And look at this. Look how much bigger it got. Well, why do you think it did that? I think, remember we learned that when air gets hot, it expands, it gets bigger, it gets more energy. I think there was a lot of air in a marshmallow. That's why it's so light. And when I put it in the microwave, it just expanded the air. And look at that. Doesn't that look great? And so what I did was I took one of those marshmallows the other day, and then I let it sit. And now all the air that's hot has gone out, and it's just sort of like a solid again. Isn't that exciting? Now remember, boys and girls, when we were talking about liquids, when we were talking about density, I put a key lime, this is a little lime, in water, and it sank. And then when I put salt in the water, it floated. Well, I'm wondering, does all fruit sink? Let's try a grape. Yeah, the grape sinks too. What about an orange? You think an orange is gonna sink? No, the orange floats. That's amazing. What about a tangerine? The tangerine floats. Now, we have to run an experiment to figure out why that is. So we have to experiment to decide, why do some fruits float? One thing I noticed is that the peel on the outside of an orange and a tangerine is sort of thick, and it has air in it because you can sort of see it does. So I'm thinking maybe it's the peel that's acting like a life preserver and making the tangerine and the orange float. So let's try it. If we're right, this will sink because it doesn't have the peel on it. We're right, it sunk. And look at the peel. The peel has a lot of little air pockets in it. And let's see if it's going to float. If our experiment is right, then this should float. Eureka! So boys and girls, why do we have to do so many experiments if we're a scientist? That's because a lot of times we think something is true, and then when we do experiments, we find out we were wrong. I'm going to give you an example. Now we know that the body contains solids, muscles, bones, and liquids, and gases. So if I were to ask you the question, what do you think weighs the most in your body, or my body, the solids, or the liquids, or the gases? We know it's not gases. You would probably say, like I would say solids, because bones are heavy and muscles are heavy, and they weigh a lot, I think. No! Scientists have run lots of experiments and have proven that in the human body, what weighs the most is water. In fact, if you get on the scale, if you go to your doctor's office and you get on the scale, and let's say you weigh 100 pounds, 60 or 70 pounds of that, more than half of your weight, is due to water. And it's because not only do we have water in our blood, but we have water in our bones, in our skin, our muscles. There's water everywhere in our body. So that's why we have to do experiments. Now, boys and girls, most solids just sort of sit there and don't do anything. But some solids are changing all the time. Do you know what they are? Think about it. I don't have any inside my house, but I'll give you a hint. Look out the window. What do you see? You see a lot of solids. Do they change or do they stay the same? They change all the time. Plants do. Now, I don't have any plants inside my house, or I said I didn't, but look what happened. I bought some sweet potatoes at the supermarket, and I didn't eat them all, and this sweet potato is starting to sprout. And can you see all the little plants that are coming out of the eyes? This is what's funny. English is so funny. All those little dots on a sweet potato or a potato are called eyes. Now I could go outside and plant each one of these, and they would grow into sweet potatoes, and I would have sweet potatoes down under the ground. Sweet potatoes and potatoes are sort of alike, seem alike. Potatoes have eyes also, and that's the way you grow new potatoes, is you let them sprout out underground. And sweet potatoes and potatoes grow underground. But this is what scientists have found. They're not even in the same family. They're not related. The sweet potato is related to the morning glory flower, and potatoes are related to tomatoes and to peppers. Isn't that amazing? And the other thing that's amazing is both sweet potatoes and potatoes came from South America and then to Mexico, and we didn't have any potatoes or sweet potatoes in California or the United States until a long time after they were in Mexico. Mexicans had a lot of things. They also have corn, and they had chocolate, which is really wonderful. Now, boys and girls, we all know that water, if we freeze it, becomes ice. We have an ice cube. And also, if you leave it sit out, I let the ice cube sit out for a couple of days, and it disappears because it becomes water vapor and just turns into gas. So we have to think, why does water act differently in these different forms? What's the difference between the water and the water vapor and the ice cube? So boys and girls, to explain why ice is different than water, we have to get a big microscope. Now, I just have a little looking glass here, and I can look at that, but I can't see any difference between the water and the ice cubes. But if I had a big microscope, a gigantic microscope, I could look at the ice and the water and see the molecules, because the smallest part of any matter is a molecule. And this is a funny word. Molecule is a funny word because it's pronounced molecule, but M-O-L-E is other words. Like M-O-L-E is a mole. That's that little creepy animal that's running around in the yard underground. They dig holes underground. And also M-O-L-E is mole, which is those little things that you get on your body. I have some on my neck. And also M-O-L-E, if you go to a Mexican restaurant, it spells mole, which is that fabulous sauce that's made out of chocolate. Everything with chocolate is good. So I'm going to pretend that I have a big, powerful microscope and I can see molecules in the ice cube. Now, in the ice cube, which is a solid, I'm using Hershey Kisses with almonds because then I get to eat them after the experiment. That's what's so wonderful about doing experiments in my kitchen. I get to eat marshmallows and chocolate and fruit. So each one of these is a molecule, and you can't see them, but they're in there. And molecules in a solid are packed really close together. And they have energy, so they vibrate, they move, but they don't flow like water does, or they don't move around like air does. So molecules in a solid, like in the ice, this is what they do. They just sit there and vibrate, and they don't bounce around a lot. They just sort of shake a lot. So that's molecules in any solid. It doesn't matter whether it's a rock or whether it's a marshmallow or it's an ice cube. And now this is the way the molecules look in a liquid when they're in the water. So they're farther apart, and they still have a lot of energy, and they bounce around, and you can move them. If you pour the water one way or you pour the water the other way, a solid, you can't do that. You can't get the molecules to move from one side to the other. So this is what molecules look like. They're still shaking, but they're not as close together as they are in the ice cube. Okay, now I've eaten some more Hershey Kisses, and look what happens. The molecules are way far apart, and they still have a lot of energy, but they just fly all around and take up all the space. It doesn't matter how big the box is you put them in, they just take up all the space because that's what air does. It just goes everywhere. So you know, boys and girls, there is a solid that's like ice, but it's called dry ice, and it's really exciting. Dry ice is just carbon dioxide. That's what the bottles are on soft drink. You know, if you shake up a soft drink and there's bubbles, that's carbon dioxide. They put that in the soft drink to make it taste good. And that carbon dioxide, if you freeze it at a very, very low temperature, very, very low temperature, it forms dry ice. You can't touch dry ice because it's so cold that it will burn you. And it's really careful. But it's fun to have because it makes a lot of really weird shapes. Wow. So boys and girls, dry ice is really fun. It's a lot more fun than regular ice. It's so cold though, you can't touch it. If you touch it, you will burn yourself, which is really weird because this way you burn yourself with something really cold, just like you could burn yourself with something really hot. But it's sort of exciting because dry ice, which is carbon dioxide, it goes from a solid, which is very, very cold, to a gas. There's never a liquid. And so you can see that it acts really funny. See how it bounces around and it makes noise and it gives off smoke. You can see the smoke coming off of the dry ice that's frozen is the gaseous dry ice, which is carbon dioxide coming off. And the funny thing about it is if you add it to water, you get all these fumes coming off. So the liquid the solid turns to gas very fast, and it's sort of spooky, like at Halloween time. Sometimes in the movies they use carbon dioxide gas coming off of the solid in water to make all this smoke. And then it does really funny. If you add some soap to the water, look what happens now. You get these bubbles blowing. It's just like when you blow bubbles with a bubble machine. It gets all these bubbles blowing out. So carbon dioxide is really fun, but you can't touch it, so that's why I don't want to have any here because I don't want to burn myself. So boys and girls, we talked about acids when we were talking about liquids, and we have acids all around the kitchen. I'm going to do some experiments with vinegar because that's a good acid. And there's another material that's the opposite of an acid, and that's a base. And so we have a base in the kitchen in a lot of places, and it's called baking soda. I bet your mom has some of this around in the kitchen. So when you mix this solid of base and this liquid acid, you get really exciting things happen. You may have done this at school where you make a volcano and then you have all this stuff spew out of the top of the volcano. Well, I'm not going to make a volcano because I don't have any boys and girls here to help me, but I am going to run some experiments that I think you're going to find they're fun to do. So boys and girls, I'm going to make a bomb. I'm going to put 1/4 cup of warm water and 1/2 cup of vinegar. I'm going to put it in my baggie. You can't have a hole in the baggie or this won't work. And then I'm going to take 1.5 tablespoons of baking soda, which is the base, and I'm going to put it in the baggie too.
It's so close, it's huge.
I know. Ah! So this experiment is fun. It's Frankenstein's hand. And so I put the baking soda, which is a base, inside a glove, a plastic glove, and in the glass I put vinegar, which is an acid. Now look what happens when I mix the two. Okay, boys and girls, we've done a lot of experiments and games with solids. Here's one I'm going to leave you with. I think it's a trick you can play on your dad. Say, Dad, can you put a quarter on top of a dollar bill, on top of an empty water bottle, and get the dollar bill out and leave the quarter on top of the empty bottle of water? And I don't know, he may try to do it and he may not be able to. And this is the way you do it. Make sure you don't put the quarter on top of George Washington's head. Put it over here on the side so you don't have to move the paper so much. And then get it right on top. And this is what you do. And the quarter stays on top. Because if you're not careful when you do this trick, if you try it like this, the quarter falls off. Ready? Mm-hmm. Quarter's there, fingers there, quarter stays there. Is that a great trick? Next time, we're going to talk about energy. See you next time. Bye-bye.